Hello students, welcome to the course on analog and digital communication systems, and the course code is EC501. This is the course for BTech 5th semester EC students. Myself, Dr. Surojit Bosak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata. And this is my official email address. Students can contact with me through this email ID. In the last class on digital modulation techniques, we have completed the coherent binary phase shift keying, including its mathematical representation, signal space diagram, error probability calculations, generation and detection techniques, and power spectra of BPSK. In this class, we are starting another type of phase shift keying modulation techniques, which is called quadriphase phase shift keying, or it is abbreviated as Qpsk. So let us start lecture number 3 from the module 5, that is digital modulation techniques. And the topics for today's class is quadriphase phase shift keying, or it is abbreviated as Qpsk, signal space diagram of Qpsk signal, and the error probability calculation for Qpsk. And the lesson objectives for the above topics are: study various digital modulation techniques that can compute the bit error performance and compare their advantages and limitations. And the second lesson objective is study signal vector representation of various digitally modulated signals by creating signal constellation. And this topic, that is the today's topic, is mapped with CO number 2 and CO number 5. So let us start lecture number 3 from the module 5, that is digital modulation techniques, with the topic of Qpsk. Quadriphase phase shift keying, or same as quadriphase phase shift keying. So first of all, it is a coherent type of phase shift keying. So BPSK is enough. Why? First of all, you should know why a new or advanced type of phase shift keying, or that is called quadriphase phase shift keying or Qpsk, is required. You know that the provision of reliable performance exemplified by a very low probability of error is one important factor or one important goal in the design of digital communication systems. Apart from that, another important factor from the system engineer is bandwidth or efficient utilization of channel bandwidth. So Qpsk is basically a bandwidth conservation modulation scheme. Here we prove that the bandwidth requirement of Qpsk system is basically half of the bandwidth requirement of BPSK system without hampering probability of error. So it is basically a bandwidth conserving modulation scheme. In Qpsk, obviously it is a phase shifting. So phase of the carrier is varied, but the question is how it is varied. Obviously it is not same for like BPSK signal. So how it is varied? So in Qpsk, the information carried by the transmitted signal contained in the phase, obviously, and the phase of the carrier takes on one of four equally spaced values. So their phase may be pi by 4, 3 pi by 4, 5 pi by 4, or even 7 pi by 4. So for this set of values, we may define the transmitted signal as square root of 2e by t cos 2 pi fct plus 2i minus 1 into pi by 4, where t belongs to 0 to t. So in Qpsk, basically the phase of the carrier takes any one value out of four equally spaced values or equally spaced phase values. What are the values? They are pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. So mathematically, a transmitted signal of Qpsk can be represented by this expression. In this expression, Fc is the carrier frequency as it was. Now here I is equal to, so I is equal to 1, 2, 3, 4, because from 4 phase you can see that there are 4 possible symbols are present. So I is equal to 1, 2, 3, 4. And what is E and T? Remember that E indicates here transmitted signal energy per symbol. Remember the difference between BPSK and Qpsk. In case of BPSK, it was EB, that is the transmitted signal energy per bit. But here one bit or one binary value actually belongs to bit. So that is why E indicates here the transmitted signal energy per symbol, and T is the symbol duration. Now here each possible value of phase corresponds to a unique die bit. And thus, for example, we may choose foregoing set of phase values to represent the gray encoded set of die bits. Here basically we transmit each possible phase values basically represents 2 bits or die bits, and that die bits basically differ with gray encoded, that is only 1 bit can change at a time. So the symbols are, or the set of die bits are 10, 00, 01 and 11. Die bits means only one single bit change from one die bit to next. Now, the signal space diagram of Qpsk. To draw the signal space diagram of Qpsk, just express the previous expression. See this expression, first trigonometric series. So cos A plus B, just express it cos A cos B minus sin A sin B. So root over square root of 2e by t cos A cos B cos 2i minus 1 into pi by 4 into cos 2 pi fct minus square root of 2e by t sin 2i minus 1 into pi by 4 sin A sin B sin 2 pi fct, where I belongs to 1, 2, 3, 4. Now see the expression. From the expression, one can easily say that for constellation diagram or signal space diagram, it has 2 orthonormal basis functions which are denoted as phi 1t and phi 2t. So more specifically, we can say that phi 1t and phi 2t are basically the 2 quadrature carriers. So phi 1t can be defined as square root of 2 by t cos 2 pi fct, where t belongs to 0 to capital T, and phi 2t can be defined as square root of 2 by t sin 2 pi fct. So in that way, we can define the 2 orthonormal basis functions, or better to say 2 quadrature carriers. Now, so these are the possible symbols of gray encoded symbols, say 10, 00, 01 and 11. And the phase, we know the phase of the Qpsk signal is pi by 4, 3 pi, say for 10 it is say pi by 4, for 00 it is say 3 pi by 4, for 01 it is say 5 pi by 4, and for 11 it is say 7 pi by 4. And two basis functions are present. That means the signal space diagram is 2-dimensional. Now, how to determine the coordinates of message points? Or here it is written as 4 message points and associated signal vectors. So that is the coordinates of the message points. For I equal to 1, for I equal to 2, for I equal to 3, and for I equal to 4. The most important thing, how this expression comes. Okay, in the signal space diagram, so for first symbol SI1, or for the first symbol for with the basis function 1, it is say S11 and S12. S12 is the projection of signal S1t along the basis function phi 2t. So how S11 is determined? We know that it is basically an integration of 0 to t s, if it is Si1, so Sit phi 1t dt. Si1 means projection of signal Sit along the phi 1 axis or phi 1 basis function, and similarly Si2 is the projection of signal Sit along the phi 2 basis function. So how this can be evaluated? You know that this can be evaluated as integration of Sit phi 1t dt. Now for Sit, or the first symbol say 10, Sit is like that, and you know the value of Sit into phi 1t, so it is multiplied by cos 2 pi fct. So that part is sin 2 pi f 4 pi fct, that part is rejected. So only cos square 2 pi fct term is present, and after integrated only dc term is present. And for I equal to 1, that means it is only cos pi by 4. So if you calculate it, it will be obviously plus square root of e by 2. Clear? Simple mathematics. I am describing you the process. Similarly, for the case of Si2, for the first case, that is for 10, Si2 means integration of Sit phi 2t dt. So Sit you know that, and phi 2t, that is a function of sine function. So first part is sine 2 theta, and it is rejected by the integrated term, and second term is sine square theta, sine square 2 pi fct. So half into 1 minus cos 2 theta, again cos 2 theta term is rejected. So here for the first case, when I equal to 1, it is sin pi by 4. So that means 1 by root 2. And obviously this negative sign present. So after calculation, it will be minus root over e by 2. Simple mathematics. So in that way, you can generate the two coordinates for each of the message signal. The general expression is defined here. Simply, this expression basically comes from the simple trigonometric expression, simple mathematics. And the say general form of the for the 4 message points, And the associated signal vectors are defined as SI is equal to square root cos 2y minus 1 into pi by 4. And for the y location, xy, two locations for each message point, and the y location is minus root over square root of e sine 2y minus 1 into pi by 4. For I equal to 1, 2, 3, 4. So for I equal to 1, say it is cos pi by 4 square root of e by 2 and minus square root of e by 2. Similar. So in that way, if you calculate for all the gray encoded bits like 0, 0, 0, 1 and 1, 1 with the phase shift of 3 pi by 4, 5 pi by 4 and 7 pi by 4, you can easily calculate the coordinates of the message points just by doing simple mathematics. So SI1 for the case of 0, 0, SI1 when the phase shift is 3 pi by 4, the coordinates are x coordinate is minus root over e by 2 and y coordinate again minus root over e by 2. For the case of 0, 1, in which the phase shift is 5 pi by 4, just 45 degree, 5 into pi by 4. And the coordinates of the message points for SI1 is minus root over square root of e by 2 and plus SI2 is plus root over square root of e by 2. And for the case of 1, 1, the phase shift is 7 pi by 4. And the coordinates are x coordinate plus square root of e by 2 and the y coordinates also plus square root of e by 2. So these four message points, how can you represent? Now come to the signal space diagram. So this is the signal space diagram of Qpsk signal. So first draw a phi 1 axis. So this is the phi 1 axis or phi 1 basis function. And similarly here a phi 2 axis is present. Just it is perpendicular to each other, orthogonal. Here we consider, normally we consider that positive turn along this, positive y axis is along this line. But here we consider this part is the negative y axis, and in the downward section is the positive side. Downward section, upward section is the negative part. Just to consider it. You can also change the rule. According to this rule, here the message points belongs. So for the first part, that is for message point 1, 0 is phase shifted by pi by 4, which is plus root over e by 2 minus root over e by 2. So message point 1, 0 phase shifted by pi by 4, so which is plus root over e by 2, and upward section, I told that upward, we consider that upward section is the negative part and downward section is the positive y axis. So this part is minus root over e by 2. So this part. So message point M1, that is for 1 0. Then for 0 0 is 3 pi by 4, that is minus root over e by 2 and minus root over e by 2. So for message point 0 0 is here, and the angle, phase angle is 3 pi by 4. So here it is pi by 4, it is 3 pi by 4. And the corresponding coordinates are minus root over e by 2 here, see, and again it is minus root over e by 2. Next is the message point 0 1, that is 5 pi by 4. So for 5 pi by 4, the corresponding coordinates are minus root over e by 2 plus root over e by 2, x and y coordinates. So it is in this circle 5 pi by 4. Now the axis is minus root over x axis minus root over e by 2, and second point is plus root over e by 2, here, and the last case 1 1. For the case of 1 1, the phase angle is 7 pi by 4, fourth quadrant. That means it belongs a fourth quadrant, and the point coordinates are plus root over e by 2 to plus root over e by 2. Both are positive. So here plus root over e by 2, and again this part is the, as I said, that this is the positive side, positive phi 2 axis. Downward section is the positive phi 2 axis, and upward section is the negative phi 2 axis. So this is for message point M4. So this is the signal space diagram or the constellation diagram of Qpsk signal. This is very much important, and this is the first two-dimensional signal space diagram still we gone through. Next is the time domain waveform. We know that there is every bit, every binary digit occurred 2 bits. So obviously bandwidth will be half. Again we will calculate the power spectra. So next we determine a time domain waveform. How Qpsk waveform can be drawn. Suppose the input binary bits are, here it is not the case for like a BPSK signal. In case of BPSK, it was just 0 to 1 or 1 to 0. There was a simple phase shift of 180 degree. But here it is not, obviously. So how you can draw a Qpsk modulated signals? This is a very important and crucial questions. Most of the students cannot able to answer this question. Suppose the bit sequences are 0 1 1 0 1 0 and 0 0. So here the first bit, that is first 0, it occurs for 2 bits. it belongs to 2 bits. So first 0 is I1t multiplied by phi 1t, SI1 multiplied by phi 1t, and second is the SI2 even. First is the odd number sequence. So odd number sequence SI1 multiplied by phi 1t, and even number sequence or polarity of coefficient SI2 multiplied by phi 2t. So first bit SI1 is the first 0, then 0 is represented here up to 2 bits, up to, that means this up to this one, and again there is 0 to 1. Then there is a phase shift is present of 180 degree, and it again holds for 2 bits up to this one. So no phase change 1 to 1, no phase change is present, this one to this one, no phase change, and then again this 1 to this 0. So there is a phase shift of 180 degree. See, here is a phase shift. So this is for corresponds to odd number sequence. Now for even number sequence, first we start from this one, even number 1, which is multiplied by phi 2t. That means phi 2t is basically sine function, sine 2 pi fct. So first one starts here, say first odd bit, and it holds for 2 bit until reaches the next odd bit, that is 0. So here 0 comes, and say 1 to 0, then there is a phase shift of 180 degree. Then again 0 to 0, no phase shift, again 0 to 0, no phase shift. So there have no phase shifts. Now ultimately the Qpsk modulated signal is basically SI1 phi 1t, that is odd number sequence, plus SI2 phi 2t. So this is the ultimate of Qpsk expression. Now how phase shift is occur for the first bit, first 2 bits? See here, in both cases there is a phase shift of pi 180 degree. That is why in the ultimate modulated waveform there is a phase shift of 180 degree in that case. Then no phase shift for 2 bits. Then ultimately here, when it comes to that point, for the even number of sequence, that is SI2 phi 2t, there is no phase shift. But for odd number sequence, there is a phase shift. So only one phase shift occurred, not both cases. So in that case, the phase shift is only pi by 2. So the simple theory is that another way to represent this waveform by just shortcut method. See 0 1 2 1 0. See the constellation diagram. Here 0 1 2 1 0. So here it is pi by 2 and pi by 2. So ultimate pi by 2 plus pi by 2 is overall pi phase shift is required. So 0 1 2 1 0, see that die bit 0 1 2 1 0, there is a phase shift of pi. But for 1 0 to 1 0, there is no phase shift, no change of points. And again for the last case 1 0 2 0 0. See the 1 0 the message point M1, 200, that is the message point M2. So 10200, here it is pi by 4 plus pi by 4. So overall phase shift is pi by 2. So from M1 to M2, that means from message point 10200, there is a phase shift of pi by 2. So simple theory is that whenever the 2 bits can change, see here 0, 1 to 1, 0. So 2 bits are changing, then there is a phase shift of pi 180 degree. And if there is a phase shift bit change, only 1 bit can change. See in the last case 10200, only 1 bit can change because of the gray encoding theory. Then there is a phase shift of pi by 2. And if there may be a chance that the bit cannot be changed, then no phase shift can occur. See this case 10 to 10. So no bits are changing. So no phase can change. So in that way, you can design or draw a Qpsk modulated waveform. Okay? Clear? Now moving for the calculation of error probability of Qpsk system. So in coherent Qpsk, the received signal xt is defined as xt is equal to sit plus wt, where t belongs to 0 to t and I is equal to 1, 2, 3, 4 for 4 possible symbols, where wt is basically a sample function of a Gaussian noise process with 0 mean and PSD n0 by 2. So in that case, the observation vector x has 2 observable elements which are denoted as x1 and x2. So x1 is defined as, say, integration of 0 to t xt phi 1 t dt. So xt means here basically sit plus wt. Now you know the x coordinates, that is see that expression, basically this expression, from this expression x coordinate, this first one, square root of e cos 2i minus 1 into pi by 4. So square root of e cos 2i minus 1 into pi by 4 plus w1 is the noise function. So if we integrate it, we can see that it is plus root over e by 2 plus w1. And similarly, for the observable element x2 is 0 to t xt phi 2 t dt. So 0 to t xt is the y coordinates plus w2. So if we integrate it, for I equal to 1, 2, 3 and 4, it will be minus plus root over e by 2 plus w2. And in the first case, it is plus minus. So it integrate for I equal to 1, 2, 3 and 4. And after that, we see that the x1 is plus minus root over e by 2. And it is for minus plus e by 2 plus w2. Now, what is the decision rule? See the constellation diagram. The receiver decides that signal S1T, that means 1 0, binary symbol 1 0. Signal S1T is received if the received signal point falls in the region of Z1. Similarly, receiver takes decision in favor of symbol S2T or binary symbol 0 0 if the received signal point falls in the region Z2, and so on. See, similarly, if receiver takes decision in favor of symbol 0 1 if the received signal point falls in the region Z3, and more obviously this is the decision region, and from what 4 regions are drawn, Z1, which are located as Z1, Z2, Z3 and Z4. And similarly, the receiver takes decision in favor of symbol S40, or better to say binary symbol 1 1 if the received signal point falls in the region Z4. So in that way, the receiver takes decision. So here it is written, decide that S1T is transmitted if the received signal point associated with the observation vector X falls inside region Z1. And similarly, the receiver decide that S2T was transmitted if the received signal point associated with the observation vector X falls inside the region Z2, and so on, so on, so on. What I am already told. Then the question is, when error occurs. Suppose that, again come to the constellation diagram. Suppose that the originally signal S40, that is binary symbol 1 1, was actually transmitted, but the noise is such that the received signal point does not fall inside the region Z4. It can fall any one of the region like Z1, Z2 or Z3 except Z4. In this situation, an error will occur, and now we want to calculate that probability of error. And similarly, we can say that if say signal S1T is transmitted, then noise is such that the received signal point does not fall in the region Z1. It can fall any one of the region of for Z2, Z3 and Z4. Then an error occurs. Same cases occurs for the symbol 0 0 and 0 1. So in this situation, error will occur. Now we want to calculate this probability of error. So to calculate the average probability of symbol error, a coherent QPSK system is in fact basically it is equivalent to two coherent BPSK system working in parallel with two quadrature carrier. So QPSK is basically two parallel coherent BPSK systems using two in-phase quadrature carriers. So therefore, signal energy per bit. Remember, here E is the transmitted signal energy per symbol, and therefore signal energy per bit, which is denoted as EB in case of BPSK system, which is basically E by 2. And we know that the noise spectral density, because of AWGN noise spectral density is N0 by 2. Therefore, the average probability of bit error in each channel of coherent QPSK system, in each channel, one channel, is same as BPSK system. So which is denoted as, say, P dash equal to half ERFC root over EB by N0, same as BPSK, and EB is denoted as E by 2 in the last slide. So it is basically half ERFC E by square root of E by 2 N0. So this error probability is valid for one channel. Now the question is how to calculate the average probability of bit error in two channel of coherent QPSK system, or if there is a 2-bit error are present. How it is calculated? Is it same or it is differ? So for the case of two-channel coherent QPSK system, first we calculate the average probability of correct decision. In the case of two-channel coherent QPSK system, maximum number of possibility for or worst case error, even 2-bit can be erroneous. This is the worst case. Now if these 2 bits are erroneous, maximum case, then average probability of a correct decision resulting from the combined action of the two channels working together. So correct decision is, say, PC is basically 1 minus P dash square, or the product of, and it is square because of the two coherent channel, or it is, say, product of 1 minus P dash. So it is 1 minus half ERFC square root of E by 2 N0 square. So A minus B whole square, by simple mathematics, it can be written as 1 minus ERFC square root of E by 2 N0 plus 1 by 4 ERFC square root of E by 2 N0. So this is the correct decision resulting from the combined action of the two channels. Then the average probability of error for the two channel case is basically 1 minus PC, 1 minus correct decision. So average probability of symbol error for coherent Qpsk system is denoted as say PE, which is say 1 minus PC, which is 1 minus, just this one is cancelled. So ERFC square root of E by 2N0 minus 1 by 4 ERFC square E by 2N0. So this is the error probability or average probability of symbol error for the case of two channel coherent Qpsk system. Now assuming the high SNR, that means E by 2N0 is much higher than 1, high SNR condition, high signal to noise ratio. In that case, the probability, average probability of symbol error, in that case, this ERFC square term is negligible. It is small if E by 2N0 is much greater than 1. So ultimate the error probability due to this occur, due to this term is small and it is squared. So it is less smaller and almost negligible. So ultimately under high SNR condition, the average probability of error for coherent, for two channel coherent Qpsk system is ERFC square root of E by 2N0, this term. So which one is less? One bit or single channel or two channel? In case of single channel, just a half piece present here. So obviously in case of single channel, error probability is less. In case of two channel, maximum number of two error can be occurred. So obviously error probability is higher than the single channel. Now we know that from the signal space diagram, which is circularly symmetric, the expression is shown when I discuss on the signal space analysis in module number 4. Since 4 message points in signal space diagram are circularly symmetric with respect to the origin, then probability of error can be calculated as less than or is equal to half k equal to 1 to 4, obviously k not equal to I, ERFC dik by 2 root over N0 for all I, where dik basically the distance from I to k. Now following this rule or following this expression, the error, we now calculate the error probability. So consider for example, say message point M1, say binary symbol 10 is chosen as transmitted message point. That means M1, that means binary symbol 10 is chosen as transmitted message point. And the message point M2 and M4, that is 00, binary symbol 00, and for M4 that means binary symbol 11 are closest to M1. So in that way we can easily determine the distance, and M1 is basically equidistance or same distance from M2 and M4. See again the constellation diagram. So from M1 is circularly symmetric. Both point M2 and M4 are equidistant, same distance, and you know the coordinates also you know. So from that coordinates you can calculate the distance also. So which is basically identified as represented as D12 and D14 is square root of 2e. Now for a high enough SNR, for a high enough signal to noise ratio, that is E by N0, the likelihood of both bits of a symbol being in error is much less than a single bit. So under high signal to noise ratio, the probability of 2 bits error is very much less than the probability of 1 bit error or single bit error. So under high SNR, we can ignore the probability of 2-bit error, and since 2 bits per symbol, so the transmitted signal energy per symbol is equal to 2b. So already I told that EB equal to E by 2. Therefore, the average probability of symbol error, just following this expression, just D12 and D14 is 2 square root of 2e, and 2e, that is 4, e means 2eb, so it is 4eb, square root of 4eb. So square root of 4eb, that means 2 come outside the square root, so it is 2 square root of eb. Now come to the expression, this expression. So it is probability of error equal to maximum case or worst case. When equal to sign comes, it is half ERFC and summation of DIK, that is 2 root E, 2 root EB. So 2 cancel, say again, so it is square root of EB by N0. Just for replace here E with 2EB. So 2 cancel. So probability of error is ERFC. Average probability of symbol error is ERFC square root of EB by N0. And with gray encoding, whenever we are using the gray encoding, which is used for incoming symbols, in that situation, the bit error rate for Qpsk system is same as coherent BPSK system, which is half ERFC square root of EB by N0. So which is same as the average probability of error as coherent PSK system. So for a fixed N0, if we increase the EB or signal energy per bit, then error probability will be less. So this is the all about the error probability for Qpsk system. So which is exactly identical for the coherent PSK system. So error probability is not differ between QPSK and BPSK. So what are the advantages of QPSK? It's nothing but bandwidth. The bandwidth of QPSK is just half of the bandwidth requirement of BPSK signal. In the next class, we calculate the power spectral density of QPSK system and prove that it's a bandwidth conserving system. And obviously, the generation and detection technique will also be discussed in the next class. So let us stop here. Thank you. Thank you so much.